So I'm doing my research paper on the classification and visualization of Alzheimer's disease using volumetric convolutional neural network and transfer learning. So the outline of my presentation is that we will go over some background information, go through a little introduction, some methods, and then the results and conclusion. A little background information about Alzheimer's disease. With the current data that we have, there are 44 million people living worldwide with the disease. Someone in the United States develops the disease every 65 seconds. Currently, it's estimated that there's 6.2 million Americans over the age of 65 with Alzheimer's. It's the 6th leading cause of death in the US, and it's also the most expensive disease in the nation. It costs $341,000 on average for health needs of someone diagnosed until death, and families have to pay 70% of the cost out of pocket. It's estimated that the total cost of Alzheimer's disease in the nation will be $355 billion in 2021, which includes $239 billion in Medicare and Medicaid payments. By 2050, someone in the US will develop the disease every 30 seconds, and it's projected that the total annual payment for healthcare, long-term care, and hospice care in the nation will reach $1.1 trillion. And here's a little introduction to the paper. The following methods are used to obtain neural images, which are used for analyzation. We have magnetic resonance imaging, known as MRIs, functional MRIs, also known as fMRI, positron emission tomography, also known as PET scans, and diffusion tensor imaging. On the top left, we have a photo of an MRI, and this provides information about the shape, location, and volume of the brain tissue. The diagnosis is made dependent on the mesial temporal lobe atrophy, which includes the hippocampus, entorhinal cortex, and perirhinal cortex, and also dependent on the temporoparietal cortical atrophy. And for PET scans and fMRI, they reveal the extent to which cells in different regions are performing by assessing how well the cells use glucose or oxygen. And glucose is also known as sugar. And they're both molecular imaging techniques. Lastly, we have diffusion tensor imaging, and it's the MRI technique that allows the interrogation of microstructural integrity. And you can see how the white matter is doing by detecting how the water is traveling. And this is based on increases in translational diffusion and decreases in directional diffusion. And damage to white matter can be assessed this way. And white matter atrophy is one of the causes of Alzheimer's disease. To slow the progression of dementia, timely treatment is crucial, which requires early diagnosis. Researchers want to find a way to increase diagnostic accuracy because traditional analytics use biomarkers based on univariate statistics. And this is under the assumption that different regions of the brain act independently. And it's not really appropriate given how current research portrays how the brain functions. Method overview. So we'll be using deep learning models. This paper proposes using an end-to-end hierarchy for the domain of the brain MRI analysis. Deep learning models allow a system to use raw data as input, allowing them to automatically discover highly discriminative features in the given training set. And this is an end-to-end learning design, basically the fundamental basis of deep learning. And the primary advantage of this end-to-end learning is that all the steps in the processing pipeline are simultaneously optimized. So this potentially leads to optimal performance. And this is one of the figures from the paper. So the levels of hierarchy are from 1, which is none, to level 4, which is full. Most existing studies currently use level 1 or 2, and they rely heavily on specific software. Sometimes they have to change parameters and manually remove noise. And due to these dependencies and seeming outliers, it makes it hard to have a fair performance comparison. Another advantage to an end-to-end learning model is that there can be a visual explanation as to why a convolutional neural network reached its classification decision. So this helps doctors and researchers understand the behaviors of convolutional neural networks and discover new biomarkers. Because in level 2, the explanation is limited to just the segmented part, which may block the possibility of new biomarkers in the eliminated regions. And in level 1, the explanation is a bit unreliable since the backward mapping to the 3D image is broken at the input level. And here's the explained method architecture. The first step is that the convolutional autoencoder-based unsupervised learning is conducted to extract sparse representations. Then the Alzheimer's disease and normal control classifier is created through supervised fine-tuning. And to construct the progressive mild cognitive impairment, also known as PMCI, versus stable mild cognitive impairment, known as SMCI classifier, the representations of the Alzheimer's disease versus normal control task are considered as initial weights under transfer learning. And lastly, the important biomarkers are localized using a gradient-based approach. A little information about convolutional autoencoder-based unsupervised learning is that autoencoders are unsupervised neural network models whose main purpose typically includes dimensionality reduction and information retrieval tasks. Convolutional autoencoders extend autoencoders and are used for image data analysis. Input data is transformed into lower dimensional feature space during encoding phase, and then the encoded data are reconstructed in the original space in the output layer during the decoding phase. And for 3D tensor X with the size, height times width times dimension, the encoder is defined as this equation. WIK is the I-type 3D filter, asterisk is the 3D convolution, B dot and sigma dot denote the dropout and the element-wise nonlinear activation functions, and phi is the max pooling. The decoder is defined as this equation, and X prime denotes the 3D construction map. W prime K is the 3D filter for decoding process. T is the group of filter types. F is the group of feature tensors corresponding to each filter. And phi prime is the unsampling. And cross entropy is the loss function used to minimize the error between the input X and the reconstructed input X prime. And it's defined as the following equation. And sigma is a set of W and W prime, and N is the number of training samples. Here we have basically the proposed way of how they encode and decode. So each proposed convolutional layers have the components convolution, dropout, ReLU, and pooling, also known as unsampling. And a padding function was used to preserve the original scale. A represents the traditional CAE, and B represents the inception-based CAE, which we'll talk about in the next few slides. Inception model for the convolutional autoencoder, also known as ICAE. To discover highly advanced representations and reduce dependency on the fully connected layer, the authors applied an inception model to the convolutional autoencoders. So the fully connected layers typically contain a large number of parameters, which result in overfitting. And instead of using a single convolution, the inception model extracts multi-level representations over the same input tensor in parallel, and then concatenates the results into a single output tensor. And since the author's models are based on 3D tensor, the result of the inception model is a concatenated 4D tensor. And inception-based model convolution autoencoders are mainly comprised of 3 encoding and decoding phases, where each proposed network model receiving input is based on the output of the previous module. So in this diagram, we can see that the author used 2 stem layers with traditional structures of convolution plus pooling in both the encoder and decoder layers. They employed a padding to preserve the original scale in the convolution and pooling process in each inception module. So a scale reduction was accomplished by pooling operations following the convolution. And to increase computational efficiency, the authors replaced the 5 by 5 by 5 convolution block with 2 layers of the 3 by 3 by 3 convolution blocks, and used a 1 by 1 by 1 filter to reduce the dimension of the feature map prior to the 3 by 3 by 3 and 5 by 5 by 5 convolutions. And the strategy of using the 1 by 1 by 1 convolutions are followed by classic convolutions. And this is known to increase the nonlinearity of the learning model compared to the conventional convolutional layers. And this helps detect more highly advanced visual representations. Here are the results. We can see that the performance for the convolutional autoencoder and inception module for the convolutional autoencoder improved around 5 to 12% and 7 to 14% respectively when compared to the baseline models. And the baseline models are the top 3 rows, and these 3 are from 3 different methods from 3 different research papers that the authors decided to choose as their baseline. And we can also see that CAE and ICAE don't do as well when there's no transfer learning involved. So I think the transfer learning is pretty critical. And here we have receiver operating characteristic curves for the different tests. The ROC curves are widely used in laboratory medicine to assess the diagnostic accuracy of a test or to compare diagnostic accuracy of several tests. And in this case, we have the method the authors use as red, and the 3 different methods are the other colors. When analyzing Alzheimer's disease and progressive mild cognitive impairment to the normal control, it does fairly well detecting accurately. And the method also does well when they test the progressive mild cognitive impairment to the stable mild cognitive impairment, and also for when they test for the stable mild cognitive impairment versus Alzheimer's disease. However, it does get more difficult when we compare the more similar conditions of stable mild cognitive impairment versus the normal control and progressive mild cognitive impairment versus Alzheimer's disease. And we can see here in the bottom two graphs that the methods perform pretty similarly for those tests. And so in conclusion, I think it's a good method to use when testing the different cognitive conditions to Alzheimer's disease, but it doesn't seem to yield more accurate results for the tests in the bottom two. And so I think it's a good stepping stone when predicting other conditions compared to not so similar conditions, but it's also important to be able to detect like these more similar conditions. So there's a lot more research to be done to become more accurate and to detect the different stages of impairments.